When neurotransmitter is released into the synapse, the cell that is receiving the neurotransmitter will have what's called a local potential. The part of the cell that we're talking about is the soma and the dendrites, or the receiving part of the cell, because a local potential is what a cell does or what a neuron does when it receives a signal. Action potential is what we call it when it sends the signal. And we're going to talk about how we get from local potential to action potential. But let's start with local first. So I've taken a section of a neuron, just the soma and the dendrites, and I've drawn it here without the dendrites because it makes it easier to see. And I've put two channels in the membrane of this neuron. One is called a ligand-gated sodium channel, and one is called a voltage-gated potassium channel. So let me say a few words about that first. A ligand-gated channel is one that opens when a ligand binds to a receptor. So this particular channel, or this particular membrane protein, has two aspects to it. One, it acts like a channel, and two, it acts like a receptor, which will bind to something specific. So the receptor part of this channel binds the ligand, and that's what causes the channel to open and allow the sodium to go through. Now this is a lot like a key being used to open a door. The key isn't what's going through the door, the key just opens it and people walk through the door. Okay, so this is called ligand gated because the ligand is what opens the gate or opens the door to the channel. The potassium channel here is voltage gated, which means that it will open in response to a change in the charge inside the cell. So here's what happens. First of all, ligand coming from the previous neuron binds to its receptor on the ligand-gated sodium channel. Sodium, because it is more concentrated outside of the cell than inside of the cell, and that's because of the resting membrane potential. Sodium moves from high to low concentration and goes into the cell. Because sodium is positively charged, it makes the inside of the cell more positive. And if we look over here at what an electrode would show us in terms of the charge in the cell, this is the membrane potential, with this being positive and this being negative. Here's our resting membrane potential. The cell is at this potential. When the ligand binds to the receptor, sodium channels open, sodium comes in, and the inside of the cell becomes more positive, is moving towards the positive end of the graph. We call this depolarization because the resting membrane potential is polarized. It is already different between the inside and the outside. And so when we allow it to become less different, it's moving closer to zero where things are the same, we say that it is depolarizing. Now, once the inside of the cell reaches a certain charge, that charge opens the voltage-gated potassium channel. Potassium is more concentrated inside the cell than outside the cell, so potassium moves down its concentration gradient from high to low concentration and leaves the cell. That means that the inside of the cell is losing positive charges, which makes the inside of the cell more negative again. And if we look at what happens on the graph with the electrode, as soon as the potassium channels open and potassium leaves, the cell becomes more negative again. And we call this repolarization because it is returning to its resting membrane potential, becoming more negative again. Now, I've written out the steps here and numbered them on the diagrams so that you can put them all together. I'll read this because I'm not sure if you can read it when the video is playing. But step 1 says ligand binds to receptor on ligand-gated sodium channel. Step 2, sodium channel opens, sodium enters, cell becomes depolarized or more positive. And step 3, depolarization causes voltage-gated potassium channels to open, potassium leaves, and the cell repolarizes or becomes more negative. Okay, so those are the steps of a local potential, It is local because it is happening just right here. It's not traveling along an axon. Now, a few things about local potentials that set them apart from action potentials, which we're going to talk about next. Local potentials are graded. That means that they come in different sizes. If a whole bunch of neurotransmitter was released by the previous cell, then a whole bunch of ligand-gated sodium channels would open, and we get a whole bunch of sodium in. It would be a stronger local potential. If only a little bit of neurotransmitter is released, then only a few ligand-gated sodium channels open, only a little bit of sodium comes in, and we have a little local potential. Okay, so that's what we mean by graded, is that they come in different sizes, different strengths, if you will. Local potentials are also decremental. The local potential is really just a measure of how positive the cell has become. And if we look at how positive the cell is here, right next to where the sodium channel is, it's going to be very positive. But as we move away from this spot, the sodium diffuses out and becomes less concentrated. Therefore, it's less positive down here. So the further we move from the site of the local potential, the weaker that signal gets. It's strongest or most positive where it starts. It becomes less positive as we move away from the source. Local potentials are also reversible, which is to say that as soon as we take the ligand away, the sodium channel closes and the local potential is over. If the neurotransmitter is released again, then the channel opens again and we start having another local potential. So it can be started and stopped and started and stopped. Finally, local potentials can be either excitatory or inhibitory. This case shows one that is excitatory. Anything that's excitatory is becoming depolarized because that's going to make an action potential more likely later on. There are cases where neurotransmitter binding to its receptor on the neuron will actually cause the membrane potential to become hyperpolarized or more negative, and that's an inhibitory local potential. These things we will talk about more when we discuss summation.